Thank you very much for all of the organizers for putting up such a nice workshop and for inviting me to it. Thank you all very much for coming to this early morning talk. My full name is Viacheslav Borovitskiy, but I typically go by Slava because it's way shorter and easier to pronounce. So feel free to call me Slava. Today I'm going to talk about actually not Gaussian random fields, but Gaussian vector fields on manifolds and graphs. Without further ado, with one note. So I will have first section which will be introductory, but it will be still close to the third of the talk in time. After this section, I would just suggest that everybody can ask any questions as we go, but throughout the first section, maybe we'll try to go through it quickly and no questions in the online regime. Okay, so let me start. Gaussian vector fields on manifolds and graphs. I want to start with a very quick recap on Gaussian processes. So Gaussian processes are a kind of uncertainty-enabled models in the sense that these are models which, beyond prediction, can give you some measure of uncertainty, which is a key word in the name of this workshop. So hopefully everybody is on board with why uncertainty is interesting and important. What is more, Gaussian processes are sort of gold standard in a number of settings for doing predictions with uncertainty. Mathematically, they are basically random functions with jointly Gaussian marginals, and the way they work as models is through the Bayesian framework, where you take some prior Gaussian process, which somehow incorporates your assumptions about the function you are trying to learn, and combine it with data to get a posterior Gaussian process, which represents your prediction and also uncertainty, which is another distribution over functions. Okay, so to get this framework going, you need to start with a prior Gaussian process, and prior Gaussian processes are determined by kernels or covariance functions. There is also a mean specification, but we will not talk about this. Typically, this is the easy part. So they're determined by kernels. Coming up with these kernels may be a non-trivial task because they have to satisfy the technical constraint of being positive semi-definite. And even if the kernel is positive semi-definite and defines a valid Gaussian process prior, the prior should be somehow good in the sense that it should represent a reasonable assumption about your function that you're trying to learn. So in this talk, I will be concentrating on defining a Gaussian process or Gaussian vector field at some point, priors or kernels, which is more or less the same thing. I will not talk about doing inference with these priors. This is a whole another topic, not for my today's talk. Okay, what is more, I will be talking about so-called general purpose Gaussian processes. Let me show you what I mean by this. So I will try to do this by example. If we take the usual Euclidean situation, then there is this class of mature Gaussian processes, which I say is the general purpose Gaussian processes in this case. So basically, these mature Gaussian processes as all Gaussian processes, they're determined by kernels. And these ones, there is just some analytic formula for the kernel. You don't need to get into the details of that formula if you haven't seen it before. It doesn't really matter for the rest of the talk. It's just that they're very explicit. But the reason why I call them general purpose is that, first of all, they define a very simple and very general assumption about the target function that you're trying to learn. That is, your assumption is basically that your target function is differentiable with a certain number of derivatives. And there is one hyperparameter of this family, nu, which actually regulates how many derivatives you have. And the second part of this assumption is that it's actually an assumption about sort of the training procedure. And it says that if you have some data and if you translate this data and rotate this data, then the model that you should get should be just the translated and rotated version of the same model. Both of them are extremely simple, general, and reasonable. And so both of them sort of boil into give you this formula. So this is why they're general purpose. And another reason why they're general purpose is that people have been using them for all sorts of problems they don't know much about, and they quite often deliver good performance. So this is just sort of two Go models for many different tasks. So one interesting thing about them is there is a limiting case of this family. So if you take the smoothness parameter to infinity, you will get the so-called RBF or Gaussian or heat or diffusion kernel, which has many names and which is particularly simple. So this is the formula. It's basically like Gaussian density. And this is the single most popular kernel or prior Gaussian process in machine learning and in statistics, I would say. And this induces the assumption of infinite smoothness. Okay, so I will consider this to be part of this Matern family for nu equal to infinity, so to say. So I will include the limiting case. Great. So this general purpose Gaussian process family works very well for inputs on in Euclidean spaces. Well, at least when your dimension is rather small. When dimension is large, Gaussian processes struggle in general, and then like the situation is very complicated. But they work very well in this case. But what I'm interested in this talk is Gaussian processes and later on Gaussian vector fields on non-Euclidean domains. And by this I mean Gaussian processes which model functions whose inputs are not vectors in RD, but something else. So for example, inputs might be points on some fixed manifold, like this donut here, the torus. Or inputs might be lying on a graph. They might be nodes of this graph or edges of this graph. Or maybe inputs might be graphs themselves. So there might be different non-Euclidean domains you are interested in setting up a Gaussian process model on. And there are different applications that sort of correspond to this domain. So for example, for manifolds, there are physical applications where manifolds arise as state spaces of dynamical systems. For graphs, well, broad networks, for example, for spaces of graphs, meaning that whole graphs are inputs. Drug design, where molecules are very often represented by graphs. So can we define somehow some general purpose family of Gaussian processes beyond RD and on all of these different non-Euclidean domains? So this is still the introductory section. So basically the quick answer is yes. Let me try to show you very briefly what are the main ideas here. The simplest approach that you can think of is maybe there is a way to generalize this same Maturin Gaussian process family to this non-Euclidean, to these non-Euclidean settings. And this is a very reasonable idea. Maybe you want to actually start with the simplest case, try to generalize the RBF kernel, look at the formula. You notice that it only depends on this Euclidean distance between a pair of inputs, and you say, well, whatever domain I'm using, there is probably a distance function on this domain, so why don't I just substitute this Euclidean distance with this other distance, like geodesic distance on a manifold, for example, or shortest path distance on a graph. Which is, again, a very good idea, but it doesn't work. The reason is there are a few results that basically prove that a kernel like this will not satisfy this technical constraint of being positive semi-definite. So, for example, for manifolds, there are results that say that there is always value of hyperparameter kappa, that this kernel is not positive semi-definite on the given manifold, unless this manifold is isometric to Euclidean space, which is sort of not a real manifold then. In some cases, you can even do this for all kappa at once. And this is actually a rather recent result from 2023. For our graphs, if you consider Gaussian processes and kernels on graph nodes, the situation is very similar, and the result actually goes back close to 100 years on this in this regard. So, and just to show you how actually constraining these results are, let me show you two examples. One example of a graph where this formula fails to define a good kernel. So this graph, just a square, already breaks it. And in terms of manifolds, this circle also already breaks it. So it's really constraining. But there is, fortunately, there is another way of generalizing that family, and so you can still obtain some reasonable general purpose family of Gaussian processes and not bump into this non-positive definiteness constraint. So let me show you how you can construct a well-defined generalization of this RBF kernel first. So to do this, I suggest that we I want to recall a fact. It says that on the Euclidean space, this RBF kernel is actually proportional to a certain p. The certain p is called the heat kernel. Heat kernel is a very interesting general mathematical object which is studied a lot. So there is this key connection. RBF kernel is more or less the same as the heat kernel. Now, let me define what the heat kernel is. So basically, it's the solution of this PDE with this initial time constraint. The wonderful thing about this connection is, well, we can use this connection and use this as a definition of the RBF kernel. And then we can say, whenever we encounter a new domain, maybe there is the analog of this PDE, this initial constraint on this domain, and then the analog of the heat kernel, and then the analog of the RBF kernel through this simple reparameterization. So the alternative generalization just says equate sort of the RBF kernel with the heat kernel, and then heat kernel generalizes on a lot of different domains. So the advantage of this approach is that you always get something positive semi-definite. I will not give you a proof now, but it's actually a rather simple thing to see. And it still also imposes a simple and general inductive bias of the same sort as the Euclidean RBF kernel does. Only now, like, translations and rotations are, for example, isometries on your manifold and automorphisms of your graph. On the downside, this definition is implicit. So we can prove all kinds of nice things about this object, but it's not always that we can actually compute the kernel. So just take two inputs, feed it into the, I don't know, into computer somehow, and get an output, a real number. So because we need to solve this equation somehow to get the generalization. But yeah, at least theoretically it's solid. There is also a way of defining the whole family of Matern kernels, which is which I'm going to show you now. So again, I'm going to use some wonderful connection in the Euclidean case, and this connection says that Matern kernel at the fixed x and x prime, it's basically some weighted integral of this heat kernel over the variable t, where x and x prime are still fixed, right? So if we know the heat kernel, we can just integrate it over this time variable t, and this will give us Matern kernel for any possible setting of hyperparameters. This is actually, I don't know, like, if you're interested, this is very much connected to the student t distribution being a gamma mixture of normals. This is basically the same thing. But yes, there is this formula, there is this connection, and there are actually a lot of other usually equivalent definitions to that, which you can use and which will allow you to define Matern Gaussian processes on other non-Euclidean domains. Actually, when I first was studying Matern Gaussian processes on Riemannian manifolds, I had no idea about this connection, and if I had, papers could have been shorter and proofs could have been simpler. But yeah, now I know, and now you don't have to go through additional difficulties. So the pros and cons are basically the same. It's always positive definite, semi-definite. It's simple and general inductive basis, but it's implicit. So now maybe the final thing that I want to say in this introductory section is, yes, so we were able to somehow generalize Gaussian processes to different non-Euclidean domains in this theoretically solid way, but we bump into this implicitness problem. This problem is not easy, but it's solvable in many cases. So this is actually something that I've been working on a lot in the past 5 years. And just to show you one particular example, if you have a compact Riemannian manifold, then the kernel can be represented by this infinite series in terms of eigenvalues and eigenfunctions of the Laplace-Beltrami operator on this manifold. And the coefficients in this series are actually extremely simple. These are just analytical expressions that never change. So as long as you can somehow get lambda n and fn, you can then truncate this summation, and this will give you at least an approximation to the kernel. The approximation, which is always going to be positive semi-definite, though, and very close properties to the ones that the original infinite sum has. So yeah, It's doable in many cases. Finding lambda n and fn is not trivial also, but also doable in many cases. Okay, so the end of the introductory section, and now I want to go to the vector fields finally. Now I want to say if you have questions that you want to immediately ask, you can. Maybe I will finish early then if there is a lot of questions, but it's not such a big deal. Okay, so let me first.
No questions there.
Oh, yes.
Like, how do you define positive definiteness or some definiteness on a manifold?
Oh, it's in the standard way, because you just say that for every finite set of inputs, x's, you construct the covariance matrix, and the matrix should be positive semi-definite. Right? So you're probably thinking about the integral type of definition, and there it's also possible, but maybe a little bit more difficult. But if you're considering this discrete definition, it's always the same. Like, you don't need any structure on your input domain to define.
Because it needs an inner product, right? So the definition of inner product would change on a manifold.
No, it doesn't need the inner product. It's just because you're just constructing the matrix of k, xi, xj, and then just analyzing this matrix, right? So the original k needs inner product, but when you generalize it, it doesn't need an inner product anymore. So yes. Yes?
Curiosity. When you're working on a graph, are you using then the Viacheslav Borovitskiy to construct this kernel?
Yes, graph Laplacian, and depending on the setting, actually, because when you say graph, it may mean different things, like nodes of the graph. If there is nodes of the graph, then yes, graph Laplacian. If there are edges of the graph, this is something that I hope to talk about at the very end of the talk. But it's Hodge Laplacian, basically, and there are also metric graphs that were recently studied, and there is like a whole other Laplacian that you can use to define the heat equation and define the kernels as well. Yes?
As far as I remember, fractional Brownian motions are well defined on manifolds and on negatively curved metric spaces as well. So
Yes.
What's
So there is, yeah, good question. So there is, actually, so I sort of said that this problem with RBF kernel, that if we just substitute the distance, it sort of says that generalizing using the distance or some similar methods, this is a no-go path. This is not the case for many people, and there is a lot of research in this direction, and you can get some models there, but frankly, I think it's much more difficult. And also the models, so for example, fraction Brownian motions are typically not suitable models for whatever we use smooth Gaussian processes for in machine learning or statistical modeling. There are some problems for them, but like if you want to use them for, I don't know, active learning, Bayesian optimization, for example, it's not a very good choice. Okay, so let me move on. Yes?
So on one of your previous slides that you mentioned that the key equation was that when you have this heat kernel, you can take the mixture, a certain mixture of this heat kernel.
Yes.
But it is also known that any radial kernel, not necessarily just a Gaussian, or the one can be written as some kind of mixture of Gaussian. So could you push this construction through, like any mixture of the general heat kernel?
Yes. I mean, basically, because what happens is that if you have a linear combination with positive coefficients of positive semi-definite functions, then you get a positive semi-definite function, right? And since this integral has a positive weight, then it basically is sort of a continuous generalization of this linear combination with positive coefficients. So yes, you can get all kinds of kernels by using all kinds of different weights. You can get, they will share this a lot of properties that you might want to use. But sort of in the beginning, I said that Matern Gaussian processes, they are sort of the result of two assumptions. One is a certain smoothness assumption, and another is the assumption of, it was basically stationarity, that if you translate and rotate data, then the model is translated and rotated accordingly. So the second one will be just carried out in the same way, because you will preserve stationarity with this thing. Of course, the smoothness will change, as we see with Matern kernels, because they're finitely smooth. RDF is infinitely smooth, and this integral allows you to get rougher kernels from this very regular kernel. But in the end, if all you're interested in is certain level of smoothness, you might not want to consider anything else but Matern kernels, because they already give you a kernel with a defined level of smoothness, and you can tweak the weight a little bit, and then you will get a little bit different kernel. But for example, if it has the same smoothness, the properties will be in practice the same, and no real reason to actually do that. Okay, so now let me move on. So now I'm actually starting to talk about vector fields. Let me motivate them by some examples. So let's look at this picture. This is a picture of a vector field. So vector field is basically a vector attached to each point of some input domain. So here we have a bunch of these arrows, and this is a visualization of a vector field. Particularly in this picture, we see the vector field of wind velocities. So wind velocities are sort of already a very important example of data and problems that you might want to solve and work with. So hopefully this already gives us some foundation of why vector fields might be important. For example, we can model wind velocities. An important thing here is actually these wind velocities, they don't live on the map. This is just a crude representation. They actually live on the sphere, because our planet is a sphere. So they actually vector fields on manifolds. So this also motivates vector fields on manifolds. But this is far from the only example, because there are, for example, ocean currents, which live on a subset of the sphere, which corresponds to the oceans, right? So very complicated, actually, domain. Or there is another very general example, force fields of dynamical systems. So basically, force is a vector. Whenever you're working with force and dynamics, you're actually working with vectors and vector fields. And this is connected to a lot of problems, for example, in robotics. Okay. So the way we understand vector fields, probably from this picture, the first intuitive understanding that comes is that this is just the same as vector valued function, right? This is what I said. For each input, you have a vector associated with this input. This is actually, this is actually quite true for the Euclidean case. It's just the same thing. So if you have vector fields on RD, then they're just vector valued functions. But on manifolds, these concepts are quite different. So you can think of vector fields and manifolds as vector valued functions for which each vector is tangential to the manifold. So it's very easy to see from the picture. Consider this hairy ball. This hairy ball is a vector function. And the reason is the hair is sort of sticking out from the ball. At least there is a component of it which is sticking out. And on the right you have vector field. It's sort of combed. So it always follows the curvature of the manifold. And this is a very important difference that leads to important geometric phenomena happening. So for example, you can notice that this hairy ball has a bald spot here on the right. And this is an example of a general theorem that says that every smooth vector field on a two-dimensional sphere will have a zero, right? And this is this zero. The zero is the bald spot. Otherwise, it's also formulated. It's also phrased as you cannot comb a hairy ball if the ball is uniformly hairy. You have to have a bald spot to comb around. So this is just an example of phenomena that arise when you go from Euclidean spaces to manifolds, and this is a motivation why we should treat this with care and not just reduce everything to a map, for example, and vector-valued functions. There is important geometry that you can lose this way. Okay, so having said that, I want to give you one recipe of constructing Gaussian vector fields. So a sort of Gaussian processes which are no longer random functions, but which are random vector fields. And which you can use to, for example, learn wind velocities. So this first recipe is simple and general, and it's called projected Gaussian processes. It's described in this paper from 4 years ago, and actually in this paper, in the appendices, there is a lot about how you actually formalize working with Gaussian vector fields, because this is a separate and interesting topic to discuss, but I just don't have time to go into this. Like, for example, how you define kernel of a Gaussian vector field. For vector-valued Gaussian process, this is typically a matrix-valued function. It turns out that this perspective is not so easy to generalize to Gaussian vector fields, but there is another which you can generalize. So there is a lot of interesting stuff going on there. Not particularly difficult, but yeah, I will not dwell on this today. So let me show you the recipe, though. The recipe is like this. Let us take a manifold, so this sphere, for example, and a bunch of scalar Gaussian processes on this manifold. Let me concatenate them together and obtain this guy, so basically a vector-valued function on the manifold. And then let me just apply the projection, which in each point x projects the vector to the tangent space of this x. And this is how you get this projected process, which is a valid Gaussian vector field. You can prove that. The projection, the main idea is that the projection is linear, so it preserves Gaussianity.
So do you have to assume that they're independent?
No, you don't have to. But also a good question. So another thing about this construction is that it's very general. You can actually prove, it's very easy to do, that you can get any Gaussian vector field using this construction. The idea is just take a Gaussian vector field, think of it as a Gaussian as a vector-valued function, take the components as these scalar fields, and do this process and arrive at the thing you started from. So if you know a priori the result, this process will just give you the same result. The problem is that it's not practical, because in practice you don't have from the start a good Gaussian vector field to talk about. What you do typically is you use scalar Gaussian processes which you have access to. So for example, you can use Matern Gaussian processes here, take an independent vector of them, and then project. And actually, whenever I will be talking about projected Gaussian processes later on, I will mean this specific practical construction. So take maturing Gaussian processes, stack them together, project them. Okay. Yeah, so these are simple and general Gaussian vector fields, easy to construct on various different manifolds, easy to work with. And actually they work pretty well as well. So just to show you what you can do with them, there is this very nice Era 5 data by, I think it's EU weather repository, something like this. And it gives you a lot of samples of wind fields on Earth. And for example, you can consider there are problems like interpolating from sparse data like this, like red arrows here, which emulates the situation where you have a satellite going around the Earth, and it measured the wind along its trajectory, and you want to extrapolate this measurement to like further away. So yeah, and I will not show you any tables with numbers now, but just believe me, projected GPs perform quite well here. But there is, interestingly, there is an issue. And this issue that you don't typically see when you use them, but you can prove that it exists. And it makes, for example, me feel uneasy a little bit about them. So let me demonstrate this on this picture. So if you take a single data point on this sphere and feed a projected Gaussian vector field to it, the result will look like this. Color here represents uncertainty. So close to this vector, it's very small, and then it's getting more yellow, so it grows. Exactly what we want to have. So now let us assume that the length scale, one of the hyperparameters, is very large. If this is the case, then when I start rotating this ball, this sphere, and for now it looks okay, but later on we see something very undesirable. So uncertainty is growing up to this point, and then it started falling. It's starting falling down after this. So it's not monotonic with respect to the distance of the sphere, which is, I think, almost always an undesirable thing to have. So yes, and this is a totally provable thing that you will always get this behavior in the limit. The reason why you don't face this problem much in practice is that, well, you typically don't have this limiting situation, and then it actually works rather fine. Yeah, but still, this was what motivated me and my colleague to try and find a more principled way of defining Gaussian vector fields on manifolds. Something that doesn't suffer from this issue. The idea is actually pretty simple because, well, let's do the thing that I explained in the very beginning. Let's use Hodge theory. This I didn't explain, but yeah, let's use Hodge theory to define heat equation on vector fields. And then do this usual thing. So it will give us the heat kernel, the vector field version of the heat kernel. In this equation, this delta is the Hodge Laplacian operator. And in the end, this will define Maturin family of Gaussian vector fields as well. And sort of theoretically, everything works quite simply. There is this ever-present difficulty of making these Hodge-Maturin, these Maturin-Gaussian processes or Hodge-Maturin-Gaussian vector fields explicit. So there is this general formula similar to what we saw before. Again, here the difference is instead of eigenfunctions, you have this Sn, which are eigenvector fields of the Hodge Laplacian. But overall, everything else stays the same, so this is absolutely the same. The difficulty is that getting those guys is even more difficult than for the scalar situation. The perfect solution would be to reduce this problem to the scalar case. So say if we know the eigenvalues and eigenfunctions of the Laplace-Beltrami operator on the manifold, maybe we can derive these eigenvalues and the eigenvector fields for constructing then Gaussian vector fields. So yeah, sometimes you can do this. For example, you can do this in dimension 2, as it turns out, because of a certain algebraic structure of dimension 2, differential forms on it, and so on and so forth. And in particular, this makes it very easy to use Hodge Gaussian vector fields on the two-dimensional sphere. And this is, I want to show a few open problems in this talk, just in case I can get you interested in working on any of them. It's not necessarily an open problem that will get you some sort of prize or anything like this, but it's just something that I thought about. I didn't find a solution quickly, nor did any of my students, and yeah, so maybe if you have any input, that might be useful. So a very simply formulated problem: can you compute these eigenfields in some neat way on the higher dimensional sphere? So just to give you some context on this two-dimensional sphere, to compute them, you just take the eigenfunctions of the scalar Laplacian, take their gradients, and take their gradients rotated by 90 degrees. A gradient of a scalar function is a vector field, so these guys give you orthonormal basis of eigenfields. And this is extremely easy to implement as well, so because you have automatic differentiation and because these scalar eigenfunctions are spherical harmonics, everybody knows how to compute those. But how to connect, for example, to hyperspherical harmonics in higher dimensions, this I don't know. And one part of motivation why this might be useful is with deep Gaussian processes that I want to discuss later on.
Can I ask?
Yeah.
That is very naive here. But this construction, it sort of forces the dimension of your vector field. Like you cannot have anything else for the dimension of your vector field, as opposed to like if you had like vector functions, where you could imagine that you have a. So you live on the manifold of dimension d, but you want functions that are on dimension k.
Oh yes. It does, but in the end you can extend everything to arbitrary k forms, and this gives you something closer to what you're talking about. So this is generalizable, but yes, what I'm talking about is it's sort of the analog of mapping RD to RD, not RD to RM.
Constrained with the tangent space.
Yes, exactly. Okay. So, but on the bright side, so we healed the issue. So if I rotate Hodge-Matern Gaussian vector field, then certainty is monotonic, unlike this guy here, and you can prove that this issue never happens. So theoretically, this is a very nice object. Practically, it's a little bit hard to work with. But in the case of two-dimensional sphere, which is interesting enough already, it's easy to work with. As a bonus of this construction, you get that you can actually take into account the interesting physical phenomena that are described by divergence and curl. So for example, for instance, what you can do is you can notice that every eigenvector field is going to be either divergence-free or curl-free, or both at the same time, in which case it's called harmonic. Then you can, and this is the illustration, so this is curl-free, so no rotational component, and this is divergence free, which is you can switch between them by just rotating by 90 degrees. You can use only one type of eigenvector fields to construct special kernels that exhibit the same sort of inductive bias, so that will correspond to only vector fields which are divergence free, or which are curl free, or which are harmonic, which is something very useful because some physical data, for example, wind at certain altitude, will be always divergence free. And something cool you can do is you can just consider this Hodge compositional kernel, which is basically a sum of divergence-free, curl-free, and harmonic parts, with each of them having different hyperparameters that you can feed from the data. The amazing thing about this kernel is, as our empirical evaluations show, it works really, really well. And it is able to detect curl-free and divergence-free inductive biases using only very limited samples of data.
Can I ask you,
Yeah.
why do you have to have the same U when you combine them?
You don't have to, but for us it just made more sense. You don't have to, you can let it go. For example, in this table of numbers, you see the divergence-free Hodge-Matern, which we explicitly sort of told about divergence-free assumption, and Hodge compositional, which did everything automatically. They reached the same result, which is very convenient. And also here you can see the projected Gaussian processes. They work well, and they actually work better than Hodge-Matern, the principled case, without any divergence-free specifications. This was actually a major pain for us when we were writing the paper, because we thought up of this principled way of defining Gaussian vector fields. It doesn't have theoretical problems. We run it on experiments, and it works worse than the naive projected construction that was around for a couple of years before. It took a lot of sweat and effort to understand why this is the case, and the reason is basically coincidentally this projected Matern Gaussian vector fields in the regime that we were using them for the data. It has the inductive bias of small divergence. Just happens to be this way. No reason for this. So, for example, if you put other data which doesn't have this property, then it would work terrible on this. So, and Hodge-Matern is trying to be sort of equitable and then treat justly all components and don't assume that divergence is close to zero. And that as a result, it performs worse on the data where divergence is actually zero. Okay. So these Hodge compositional Matern kernels, they do best and are easiest to use. If you want to use them, something in practice, my suggestion, just use them and don't think about stuff. Another open problem in relation to these Gaussian vector fields is, at the beginning I sort of started by just giving you this Hodge Laplacian and Hodge theory to generalize the heat equation, but this is not the only way. There is also an object called connection Laplacian, which also operates on vector fields, and which you can substitute in the heat equation just as well and get another notion of heat kernel. It is actually another notion, so they're not, they do not coincide. And something that I don't know of is what really changes in terms of properties of Gaussian vector fields when you do this, and how to compute the kernels when you're using connection Laplacian. It's and the reason why we chose Hodge Laplacian actually is that it was easier in terms of computations than connection Laplacian. Not a lot of thinking went into the properties, although the properties are nice in the So yeah, maybe one last thing that I want to tell you about is about the far-reaching applications of these Gaussian vector fields, a way of building a way of building deep Gaussian processes on manifolds. This is a very general application. This is why I want to show it to you. And it looks like I will not be able to talk about graphs later today, but it's okay. So the idea is super simple. If you want to construct a deep Gaussian process on a manifold, you face a big issue that your intermediate layers should map in manifold input to manifold output, which seems like, which is a very tough thing to do with Gaussian processes. Manifold inputs are already not so trivial. Manifold outputs are very, very hard because it basically goes in conflict with the whole concept of Gaussianity, which is Euclidean. There are some methods for doing that, but it's not easy. And having this at the same time is even more difficult. What I want to say is, if you have Gaussian vector fields, you can go around this issue and construct a very neat structure for deep Gaussian processes on manifolds, which actually turns out to perform very well in a bunch of applications. So the idea will be, instead of constructing a manifold to manifold map, construct a vector field that models the displacement, the small displacement of the current location to the location that it will have in the next layer. And then use exponential map to map it back to the manifold. So this concept, like, since we're using exponential maps and vectors, this is supposed to work best when everything is local, so vectors are small. But this goes very well with the concept of deep Gaussian process, where you want every layer to do some small thing. In the end, everything comes together very nicely. So yeah, this notion of Gaussian vector fields allows you to get around this issue of building manifold to manifold Gaussian processes by using this residual deep Gaussian process structure. They're called residual because every layer models this small displacement or residual, in that it's similar to residual neural networks.
Can I ask you,
Yeah.
I mean, if you have time, can you be a bit more specific about how you do these residual things? Because I didn't understand.
So, okay, you have inputs on your manifold, and then you build a vector field on this manifold. Now you have a function which maps a point to a manifold to a tangential vector. And then you apply exponential map, and it turns this function into a map from manifold to manifold. Then you combine a bunch of these together, and this gives you this multi-layer structure. Then if you assume that your vector fields are Gaussian vector fields, then this is a prior. And then there is a whole topic of how to do inference with them, but you can, and yeah, that's it.
There is no residual in your story.
The residual is because basically, since you are feeding the previous layer into the next layer as basically the mean, you are always modeling the residual with respect to the identity map. This is one way of thinking about this. Okay, so just to show you how it might be useful, if you have complex functions, like this one with singularity, we have anecdotal evidence that it gives a huge boost in Bayesian optimization to use these deep, residual deep Gaussian processes, like here. At the same time, if you have nice and smooth function, it doesn't make any difference. Which leads me to another open problem, which is apply this stuff for real-world robotics examples, and more specifically, there was this paper by Jacquer in 2022 where they applied maturing Gaussian processes for optimizing robotics control policies, and you can just, in principle, plug this in there and see if it helps with more difficult functions to optimize. Also, of course, you can use this model to work with wind velocities. And here on this plot, I'm showing you the mean prediction and uncertainty of the Gaussian vector field. The key thing is it does something that shallow Gaussian process can never do. Despite the data being rather uniformly distributed along the planet here, uncertainty is not at all uniform. Uncertainty depends on your y's, and uncertainty is high in the regions where, for example, two wind frontiers collide, and the behavior of wind is very chaotic and hard to model. Uncertainty is high along the coastlines. Uncertainty is high in India because this is monsoon season in India in this picture. So it is able to capture these phenomena that cannot be only captured by axes. So this is this picture we are very proud of in this paper because the uncertainty is so well interpretable. Also, it performs much better than shallow Gaussian vector fields for denser data. Yeah, this one I maybe will skip, and the rest is about graphs. Let me just say one thing here. It turns out that you can connect vector fields, the notion of vector fields, with functions on the edges of a graph. And then if you do this connection, it turns out that everything translates. So there is Hodge Laplacian on this edge functions. There is notion of curl and divergence, and you can do Hodge-Metron kernels, and you can do like divergence-free versions of them, and Hodge compositional kernel, and everything like this. And then you can use it in a number of different applications. So this part I will unfortunately have to skip. And maybe as one last thing, as usual, I want to advertise the library that I co-created where we implemented much of the stuff that I was talking before today. So these geometric Gaussian processes on manifolds, on graphs, on meshes, even on some spaces or graphs. So currently it does have graph edges case, which I didn't have time to talk about. It doesn't have Gaussian vector fields, which is a little bit embarrassing given the talk is about them. But sort of another open problem is if you want to code something up, consider doing a pull request. We're very happy about it always. And yes, thank you very much for your attention.
Thank you very much. There is some time for questions.
10 seconds.
What's the intuition for the non-monotonicity of the projected kernel?
Basically, the fact that projection kills something, and not always it kills a redundant portion of your prior vector function. This is the simplest way in which I can describe it. But you can do this as an exercise. Just write things out. It's not very difficult to see why it happens. And yeah, the proof is also in the paper.
So is it because you project the covariance?
Yes, I mean, when you project the sort of vector function, it corresponds to projecting the covariance as well. And then, yeah. Yes?
Thank you for the talk. About the open problem 1,
Yeah.
You have fairly different ways. The question is to solve the eigenfunction problem in two-dimensional sphere.
For the two-dimensional sphere, I can solve it for both scalar and vector field case. For higher dimensional cases, I know how to do this in scalar case. This is classical spherical harmonics or hyperspherical harmonics, but I don't know how to do this for vector field case. Yes?
So you were showing talking at the beginning of the like regression problem. So now you're using a prior in a regression problem.
Yeah.
So if you were looking at Gaussian persistent regression, then you had rates of convergence and contraction rates. For vector fields, do you get the same results, like or not so much? Or would it be the same
Open
story?
problem number 4 or 5. This. No, I didn't study any rates. To be honest, I feel that the results will just translate from the scalar case, but maybe there are some phenomena that will arise there. I didn't really give it much thought, to be honest. So a good project to do, maybe.
Any other question or comment?
So in this plot where you have the uncertainty depending on the y's, how does that happen? Because when you just have a GP, it doesn't. So how can you make sure that that uncertainty is meaningful?
Oh, I mean, like you don't have guarantees. This is the thing. This is the trade-off with deep Gaussian processes. I mean, like there is a lot of trade-offs with them, and I am actually myself typically reluctant to ever use them or study them. But as it happened, this thing actually surprised us because it works very meaningfully well empirically. In terms of guarantees, I have no idea how to provide guarantees here. Yes?
So what's the computational cost for implementing this? Because like for me, the deep Gaussian process were like hassle for the implementation.
Yeah, so it's quite doable. I think because we have actually good, very nice implementation, thanks to Kacper Biwał here, who is cited, who is a super brilliant student, taking this thing from his undergraduate project to ICLR oral paper. Basically, it uses variational inference for inference, and it uses these Fourier feature type of like interdomain features, which actually allows you to do things very, very quickly. And one open problem that I didn't show was about using the fact that it's so quick to use variational inference here to maybe leverage it for Euclidean data. Because this is what was done 5 years ago for shallow Gaussian processes, where they basically mapped Euclidean data to the sphere to use Fourier features, the special kind of Fourier features on the sphere, to speed up variational inference in the shallow case. Why don't we do this on manifolds? Well, we tried. It turns out that it's much faster, but the performance is much worse. And so the question is, can you fix it somehow? I don't know how to fix it. But maybe, for example, using Hodge Gaussian vector fields would help. We couldn't use them because typically when you use this, you project to higher dimensional hyperspheres rather than just to the two-dimensional sphere. And so since this is a better model overall, maybe you could get better performance in the end. But yeah. Maybe I'm also around during the coffee break. I will be very happy to talk about this. So thank you all again for your patience.
So thank you again.